Hello everyone, I'm Preetham. Welcome to the TS session for the week 6. So in for this week, basically I think whatever you guys were taught, like that was mainly based on the ballistic transport, diffusive transport, and some kind of conductance, and those things were the part of this week. So I'll try to cover a few things so that related to the assignment questions. As you know, I cannot directly discuss the assignment questions as per the terms and conditions. So the thing is, I can only clear some of the concepts. If you like, if you are facing some issue, like for that I have prepared some sample questions and some slides which will help you to clear few of the doubts, I guess. So feel free to ask any questions. You can stop me anywhere if you find any difficulty. So yeah, and I will quickly share my screen. I hope it is visible. 1 second. Uh, I guess it's so basically how electron flows inside a conductor. That is our main cons that like point of interest. So based on that, basically theorists and also experimentalists come up with some formula and theory, like how the transport is happening inside a conductor. So basically, 1 second, let me, yeah, I hope my pointer is visible. So uh, this is a conductor. So this is a conductor of having length L and conductivity sigma, and it has a cross section of A. So now if we connect this conductor, I mean both the ends of the conductor with a battery. So because of the driving electromotive force, you will know, so charge will flow from one end to another end. Right, so the electric field inside that has been developed because of the applied voltage is basically equals to V over L, and the current density is equal to sigma E, that from the Ohm law, as you know. So the current is basically the area multiplied by current density. So that is the number of charge carrier that is flowing per unit time. So that is called the current. So if you now substitute J by sigma E, we were having this. And finally, we get the like exactly this is the conductivity, which is proportional to 1 over L. I mean it's directly inversely proportional to 1 over R, right? So G is equals to 1 over R. This is your conductivity in the system. So as if the resistivity of the system increases, so conductivity will decrease, as you all know. So this thing basically depends on certain parameters, certain conditions of the system, like temperature, the material that we are using. So basically it will depend on that those things. So now how basically the power is dissipated in the conductor. So the amount of power dissipation we can easily calculate from here. So from EM theory, basically we know the power dissipation per unit volume of a resistor is JE, right? It's coming from the E cross B, and like not B, I mean it will be proportional to E square if we substitute, right? So that is J square over sigma. So the power dissipation in the entire register is proportional to is equals to I square over G if we simplify this whole thing. Okay. Next, so what is Ohm's law? That we need to know. It's very basic, as you know, so undergrad college topic. So Ohm law states that electric current is basically proportional to the voltage and it's inversely proportional to the resistance, right? So if we just quickly check the mathematical formula, this current voltage relationship can be written as V equals to I over IR, right? So here V stands for voltage, I stands for current, and resistance stands for the resistance of the material. So the formula can be written in order to calculate the resistance, as I already mentioned, R will be V over I. So there are some limitations of the Ohm's law. Like in certain cases, you cannot directly apply the Ohm's law in a straightforward manner. So these are the some limitations. Like firstly, Ohm's law does not apply to unilateral electrical components such as diodes. So these are basically like non. So the IV characteristics associated with the diode is completely non-linear, right? So I will do one thing. I'll also use one second. I'm switching to my tab because so that I can basically explain you in a better way. So so yeah, so I'm sharing the screen from my iPad. So I hope it's visible, right? Yeah. So see, I mean, this is so V equals IR. So you can see if I clearly plot the V over I characteristics, if I apply some current, so this is my, let's say, voltage that we are getting. Suppose we have a resistance in the circuit. Suppose we connected material, the resistor with the battery. So this is the voltage that has been applied across the resistor. So the if the current what is flowing through the resistor is I, then the resistance will be V over I according to the Ohm's law, right? So this R is basically is a so it should be function of L over A. So what does it mean? So we have a conductor which has a length L and it has a cross section of A. Okay. Then basically what does it mean? So R is proportional to L when A is constant. Okay. And proportional to 1 over A when L is constant. So this rho is called the resistivity of the material. Resistivity of the material. So it basically depends on the material, right? But it's basically a function of temperature. So at fixed temperature, we have a constant resistivity in the in the circuit. So it's like power series expansion we can do. So this will be one thing, one T, and then rho naught, like simply T square. You can do this thing in this fashion. So this is the resistivity. It depends on the temperature of a material mainly. Otherwise, it remains constant for a fixed material. Okay. So yeah, so I was trying to tell you key for, see, this is for linear material. So linear IV. So this is this is basically linear IV, right? Linear IV characteristics. So the slope of the IV curve is del V del I, right? Which is basically the resistance. So that is why it's called linear, right? Now, what do we actually mean over by non-linear IV? IV. So let's say we have a, for a diode, as we know, if we connect simple diode, PN junction diode. So this is called PN junction. You all know this, right? So it has some critical threshold voltage, right? So you can see key as we start applying bias, as the bias increase, suddenly at some point. So this is called the knee voltage, right? This is knee, one sec. This is knee voltage. So after at this point, voltage actually the current increases non-linearly. So that is why it's called non-linear IV. Right. This is the forward bias condition. This is forward bias condition. And this is your like negative, the reverse bias. You all know these things. Reverse bias condition, right? So this is the example of the nonlinear IV, as I was telling. So yeah, I'm stop presenting from the second device. Now I will present from my laptop because in laptop I don't have the touch screen, so I can't do anything there. So yeah. So yeah, I was here basically. So for the diode or the transistor also, you can see they only like is a non-linear component if is present. So also, secondly, what are the other limitation? Like voltage level will not be consistent with respect to time for non-linear electrical components with properties such as capacitance, resistance, and so on, making Ohm's law problematic to apply. So we'll deal with some examples like this, a water voltmeter. It is an example of unilateral network, and Ohm's law is not applicable for such networks, right? Also for the semiconductors such as silicon, germanium, do not obey the Ohm's law. It's basically that's why they're considered or known as non-ohmic conductors, right? Yeah, so some problem, I think. The screen got, it's getting hacked. Yeah. Um, I hope my point. Yeah. So this is one of the examples, right? Where we cannot. These are the examples. Uh, these are the fields like materials. We cannot apply the Ohm's law. This will not obey the Ohm's law. So then, this is kind of a few sample questions that I've prepared. So let's say we have a conductor that follows Ohm's law under some specific conditions of voltage applied and the current. So let's so yeah. So as you can see here, so what is the increase in the current for every 2 volt increase in the potential applied? So four options are there. First one is 1 amps. Second one is 2 amps. Third one is third amp. And fourth one is depends on the quantities other than the quantities provided. So to solve these questions, first, as I mentioned, key what is you need to know for linear materials like with the conductor which is following the Ohm's law, we can simply use the formula of, I mean, how the voltage will be related to the current. That is simply V equals to IR, right? So where R is the resistance of the conductor and resistance depends on the shape, size, and the material of the conductor, as I already mentioned and told you guys. So these are the limitations, right? Ohm's law is valid over a large class of materials. There do exist materials and devices used in electric circuit where the proportionality of V and I does not hold. So the relation between V and I is not unique. There is more than one value of V for the same current. So I can see the plot, right? So this region is called as nonlinear region. This is called the negative resistance region because as you can see, if you take the derivative of, let's say if you do take at least di dv or dv di, the slope is basically negative. That is why the resistance is negative over this region. Now see the deviation that is occurring are one of the following types. So basically V is not to be proportional to I, right? For some range of voltage or I, whatever. So you can see it has started getting deviated from after a certain point of certain current, right? It's no longer following the straight line path. So this is nonlinearity that is present in the IV characteristics. So the relation between V and I depends on the sign of V. Reversing the direction of V, keeping its magnitude fixed, does not produce a current of the same magnitude as in I in the opposite direction. So basically the explanation will be like as according to the question. So change is the del V is 2 volt, right? Where del V is just a change in the potential. So it's simply gonna use V equals to Ri. So take the del, I mean the change in the voltage on both the sides. As I mentioned, for a fixed material, fixed temperature, this R, I mean material for fixed shape and size, this R is not going to change, right? It will change if we change the length of the conductor, area of the conductor, as well as the resistance of the conductor. So why the temperature of the conductor? So why temperature? Because as I told, the R is also related to the resistivity. That resistivity basically depends on the temperature. So now what will be the delta? It will be 2 over R. So we need R, the resistance, to find the change in the current per 2 volt change in the potential applied. Therefore, option 4 is right. So it will be right. Okay. Next is which of the following metals or compounds do not follow Ohm's law? So it's simply germanium arsenide. Why? Because all the three, gold, silver, and copper, are metal. For metal, we can easily apply Ohm's law. This is they have the linear IV relationship. But germanium arsenide is a semiconductor. Specifically, this is compound semiconductor. They will not follow Ohm's law. The IV characteristics for this type of semiconductor always nonlinear. This shows the nonlinearity in their IV relationship. So option 4 is correct. So let me check once. Yeah. So three types of transport we get to see. One is diffusive, another is ballistic. Mainly, I mean, two types, but also quasi-ballistic is also there. So in this lecture here, we discuss the classical and the quantum effects caused by the ballistic transport. As a reminder, the transport can be a diffusive also and ballistic. And the parameters that determine whether you are dealing with diffusive or ballistic transport are primarily the comparison I mean between the mean free path L, right? This is very important. So this is the main free path when its system is L is small, L compared to the system size as the length and wide. So for the diffusive regime, electron would experience many scattering, right, as usual. So that is traveling through this wire depicted here. And in a ballistic regime, the trajectories are strictly uh, I mean, specular as the electron crosses the wire. Quasi-ballistic regime is something in between. Yeah. So as you can see in the picture, the electron crosses the wire. Okay, in between. Yeah. So now move to the next slide. Yeah, so now we'll discuss the Drude model. This just get to us all on the same page. We start by reviewing the classical diffusive transport, which is well, diffusive transport, well described by the Drude model. In the Drude model, as you know, in the Drude model, electrons travel at a very high instantaneous speed through a material such as metal conductor. However, materials such as, I mean, they are average motion, right, is described by the drift velocity, which is linearly proportional to the electric field or the voltage. To this, apply the sample and the coefficient of proportionality is called the mobility. That's what is has been shown here. So it's defined like this. It depends on tau. It's this characteristic time scale for the scattering time, you can also call it. And so related also to the, it's also related to the mean free path, as you can see here, and the effective mass of the electron, which can be something different from the electron mass, actual mass. So when you are in a band structure, such as a semiconductor, uh, I mean, and so from this formula, uh, by, I mean, dividing the current by the electric field that we are applying. So we define through the conductivity, the current is nothing but the density of electrons, then the electron charge times the drift velocity, right? And so from the formula above, we get the conductivity will be proportional to the density and the mobility, right? So next, considering, I mean, so this is a useful way to look at the exact same expression, but using the particular example of density for a two-dimensional electron system that we encounter. So basically very often for this course, right? As you know, the density in this 2D. So it's basically proportional to the square of the Fermi momentum, that's Kf, with a coefficient GS, right? As you can see, this is standing for the spin or the spin value degeneracy, right? Whatever you material have some may have, and the mean free path would be a Fermi velocity times the scattering time. So VF times tau will basically substitute all that into our expression for the conductivity. So we get the expression below here, from which we pull out of this coefficient to the E square over H, and basically that becomes a prefactor to dimensionless ratio, this thing of, yeah, the mean free path once again. Yeah, it depends on that. So this d now, this d is a sort of a distance between the electron uh, inside the material. So kind of a wavelength of an electron, the Fermi wavelength. And so this is a very nice, because this formula uh, contains this I mean, very important quantity, the conductance, right? So the conductance quantum basically, and it shows that if this quantity will play an important role, if this ratio here, the ratio is there, right, is getting anywhere close to one or maybe, I mean, one or more. So, very ballistic regime, right? So next is the Einstein relation. So the same expression can be obtained from the diffusive point of view. So that I'll show here. I mean, that is described by basically Einstein relation in this context. I mean, in this approach, we view the electron transport as a diffusion of the electrons. from a region of higher density or higher chemical potential to the lower density, I mean lower chemical potential region, right? So that can be created by the voltage applied to the sample. And so this extra electrons here will try to occupy these states, uh, spaces on the right, that has been shown here. So in this approach, the important quantity that describes the transport is the density of the electrons, right? In this window of chemical potential difference between the, I mean, EF, that you can see this is the Fermi energy, and EF1 and EF2, that's the difference. So the density of states for the 2D case is a constant. So in the 2D case, it's a constant, right? As I mentioned. It's a constant described that. So if we substitute that into the conductivity, we can just simply rewrite the previous expression, pulling out of this density. And after a very simple math, we get that conductivity in 2D. that is proportional to the density of states in 2D times the diffusion constant. And this expression can also be generalized for a 2D and 1D, and also for 3D, right? Which has the same functional form. So next is now in this case of ballistic transport, this is not simply a matter of the ratio parameters you can observe, right? I mean, fundamentally, that's different effects that you would never be able to observe in a diffusive case. So in a diffusive case, pretty much Ohm's law, I mean, it's a formula describe all everything, right? But when electrons are allowed to fly in straight lines for large distances, you can see very interesting effects such as electron focusing described here in this slides. So in this experiments which is done and developed, they have used uh, two openings in two-dimensional electron gas. As you can see, it's called the injector, and the one is the detector. And these are created by electrostatic gates. These are the gates. This one and this one is the gates, the shaded regions, and on top of the two-dimensional electrical so electrons live 100 nanometer below the surface of the semiconductor. So gets defined constriction, right? And through this constriction selection can be injected into this region. Okay. And voltage is measured across this side. Uh, so this schematic of the experiment is shown below. For example, here on along the green path that you can see here, the current is applied from this region here, and the voltage is measured across. So from this contact to this contact. Okay. So uh, con these two contacts are pinched basically. That what you can see here. So they are very narrow, and this is a non-local measurement geometry. Okay. In other words, geometry in which the path of the current does not correspond to the path along which the voltage has been measured. This is the famous example of this is a Hall effect measurement, right? In this non-local measurement geometry, we can observe a very interesting effect called electron focusing that I told you. So, which occurs when magnetic field is applied perpendicular to the plane of the drawing, right? Which is here to the sample. So when magnetic field is applied, the out of the plane facing up, the electron trajectories form a cyclotron, right? Cyclotron orbits. That's pretty obvious. So they become circular rather than straight line. And because there is absolutely no scattering in this two deck or a small amount of scattering, electrons really make perfect circles as they travel, and then they scatter off the gate here, and they can bounce once more. Sometimes they bounce three times. That is determined by the magnitude of the field that is applied here in the graph that is shown here, that you can see. On the x-axis, we have the magnetic field going from positive to negative. And so on the positive side, whenever the period of the cyclotron orbits matches the distance between the injector and the detector, we expect to observe a peak, right? Voltage that we measure means that the electron fly into the second hole and create higher chemical potential. So behind this constriction, which translates into a voltage that can be physically measured in this circuit. So the sequence of this peaks basically presented here, and that represent the first, the second, third cyclotron orbits shown here. Now, if the field is applied in an opposite direction, actually the electrons never reach the detector, never reach this hole, because they are focused away in this direction, and they never find this connection. So charge is not accumulated on the detector side, and no voltage is created. Okay, so this is represented by a featureless line, as you can see. Lines for the negative fields. Now this slope, uh, so this corresponds to whole voltage for or a small whole voltage hole that is detected and admitted in the geometry, because the source and the drain contacts are crossed in this non-local measurement. Okay, so, and below here you can see the actual experimental data where for the raid for the raid trace, the situation matches the theoretical prediction. So the collector is on the right side, and we can see a series of peaks for positive fields and featureless slope, a Hall effect for negative fields. And the green trace is when the source and the drain contacts were switched. So voltage was measured here, the current was measured here. In this case, conductivity completely reversed. And that represents a very important principle called mm, the time reversal symmetry, that you know, or enzyme relation described by this formula, and this one. Okay, uh, by Bob. Another thing that you might notice in this data is that peaks are not perfect. There is some structures. There are multiple peaks that you can see here, corresponding to each large peak. Now that could be because the transport in the sample is not perfectly ballistic, but there was some residual scattering, creating a couple of different trajectory that you can see paths. So, I mean, creating the structure in the pings. So this was an example of classical ballistic transport, right? Classical ballistic transport effect, for which ballistic of the transport of the electrons is essential to observe these effects. It's really beautiful demonstration of ballistic transport actually.
Yeah. So there are many different versions of the of these experiments, uh, done also in regular metals, not in superconductors, semiconductors. Originally, it's been resolved, focusing and etc. So, but uh, for most of the rest of the lecture here, I mean, we'll focus on the quantum effects related to the ballistic transport, and we'll consider the simplest solution situation basically, where transport from one dimensional constriction in the same material system, two-dimensional electron gas made of gallium arsenide, aluminum gallium arsenide. So here in the slides shown in a little more detail once again, on the surface, we have the electrostatic gates in the red that has been mentioned here, and down here below, this is where the two-dimensional electron gas is found on the surface, on the interface of gallium arsenide and aluminum gallium arsenide. However, when the negative voltages are applied to these gates, two-dimensional electron gas is restricted only to this narrow gap that you can see. The gates are determined by the electric field profile and field profile lines, and the penetrate down into the sample. So the view from the top, it can look something like this constriction, this one in a bulk to the semiconductor is to create a very narrow gap of other 250, I mean 200 to 300 nanometers, uh, through which electron can pass from the left to the right. Okay, now it's very important to consider some of the numbers related to the material system. For examples, like for a density of few times 10, I mean 10 to 15 in SI units basically, or 10 to minus uh, 10 to the minus 11 centimeter squared. The Fermi wavelength is actually not so small. It's 10 tenths of the nanometer for this particular, okay, value. They calculate the 42 nanometers, and this is comparable to the width of the constriction, right? So when the wavelength is comparable to the size of the object, we do expect to see the quantum effects, right? The mobility in these samples is rather high. Two-dimensional electron gas, the ballistic with the and it's ballistic with mean free path of tens of microns. So the mean free path here uh, greatly exceeds the constrictions, right? Constriction size. So this is an example of quantum ballistic device. One-dimensional constriction. This you can see because the gates here have this tempered shape that you can see, right, with a very sharp tip at the end. The actual confinement potential in the narrowest part in a two-dimensional electron gas is a saddle point potential, right? This one. So in the two-dimensional case, X and Y, the confinement potential is the characterized by the narrowing in the X direction and the saddle point in the Y direction. Now, because this is a quantum system, we'll demonstrate now that inside this saddle point, quantized levels will be formed. and they will lead to very important modifications to transport. So they will lead to, I mean, so this transport indeed, when a gate voltage was swept in this samples, and these are original data from the just from the 80s printed, and whole printer what they have observed is as they made the gate more and more negative, the resistance of the structure dropped as expected, right? As you can see here. So as I guess, because the structure was becoming more and more narrow, so more and more trajectories who are being reflected from the constriction. However, at some point, they will start to resolve this what to say this very regular modulations, right, in the conductance, in in the resistance. There were steps that you can see of increasing resistance as, and they increased not in integer quantized value of the resistance, but when the curves were inverted, and and instead of resistance they have plotted the conductance, the inverse of the resistance. Basically it's called the conductance. It all made sense because these steps are lined up perfectly with the quantized values of conductance. The values of 2e squared over h for this one, okay, is a factor due to spin degeneracy, right? So they have observed quite a few of these steps, more than 10, and this corresponds to a very strong departure from the Ohm's law, and drew the model, which would predict that the resistance of such a structure should just increase monotonically as you make the constriction more and more narrow widths. So now the explanation for this I already alluded to this quantization, right? Of the transverse mode. 1 second. The transverse modes has electron waves travel through this constriction pretty much from the point of view of electrons, because the wavelength or the quantum wave function dimension of the electron is comparable to the width of the quantum point contact constriction, right? Which is W. As we pinch off the constriction all the way to zero, we observe adding quantized levels to this constriction, very similar to a particle in a box problem, right? So in other words, two-dimensional density of states that lives in the leads of the two-dimensional electron gas that splits into 1D subbands, starting from the first subband. Here you can see a subband to the second subband and third subband, right? And so on. So these subbands get occupied as a formidable process through more and more subbands as the constriction is open. Uh, so proper treatment of this problem, because the confinement is a little bit smooth, is to solve the Schrodinger equation very simple in 2 dimensions times the y, I mean dimensions x and y, and to include the saddle point potential in the x dimension. It can be approximated by a parabolic potential here. Okay, which would yield us the following for the classical width of the contact. So the Schrodinger equation would result in this very simple spectrum, basically a harmonic oscillator spectrum, and so from each value of n, we'll have a dispersing quantized sub and dispersing in the y direction, as you can see, where n equals to 1, 2, 3, and so on. So now to derive the conductance quantization, we need to calculate the current that goes through this one-dimensional subbands, right? For that purpose, we apply a small potential difference. V in 1 second. Just mu1 and to the mu, and so mu1 to mu and to the left to right of the sample along the y direction, and the current is nothing but once again the density of electrons times the charge times the velocity, right? So the density of electrons is the one-dimensional density, which is given by this expression, and turns out that the velocity of the electron is in one dimension, is given by this quantity, right? While the density of states in one dimension given by the quantity, and the two quantities are in inverse of each other. So the product of the density to velocity only for one-dimensional system, when you multiply the density, the multiply the density by the velocity, you actually get a constant that is origin of the conductance quantization, right? Because when you sum up over all these conductance, subbands, what you get is that the current is proportional to 2V square over H times voltage. And if your subbands have finite transmission, you have to add up all the transmission here of all the subbands. So the conductivity is then in times this 2 times squared over the h, where is in the number of the occupied subbands. In the example here it's like 2, and some final transmission coefficient. The final transmission effects can be included, but for transmission of unity, for perfect transmission, conductance will just be given by n times 2 square over h v square, right? So now there are limits to this conductance quantization. So yeah, so as I was telling, key there are limits to this conductance quantization. It's not perfect one. Way to destroy this potential perfect quantization is to increase the temperature. This is what is shown in this plot. As temperature goes from zero point 0.3 Kelvin to the 4.2 Kelvin, uh, the plateaus are essentially washed away. Um, that you can see. The explanation for this is that for finite temperature, we have to consider a finite occupation of the energy levels. And so when we calculate the current that is going from left to right, we cannot just take a sharp cutoff, right, and say that it's proportional to mu1 minus mu2, but we have to include the Fermi distribution function for the mu1 equals to this, I mean, v plus b, and for the mu2, right, that is equals to just the Fermi distribution of E, so on. The end current uh, becomes proportional to the derivative of the Fermi energy. Okay, by the Fermi distribution, by in Fermi energy and the width of the derivative. of the Fermi distribution is of the order of 3.5. Okay, 3.5 kBt. So if you take a derivative of this function, we'll get a peak, which is something like 3.5 kBt centered at chemical potential, and that this width of 3.5 kBt would then be width of the transitions between the even plateaus and the odd plateaus. So between consecutive plateaus, when the temperature becomes large enough, we'll not be able to resolve the individual plateaus, right? Plateaus. So the individual plateaus that can be resolved at higher temperature. So you will just see the transition from one plateau to other plateau because you are broadened by this temperature factor. And since we brought the Fermi function into the discussion, it's also important to note that in this highly ballistic quantum system, there are particles going both ways, the particles going from left to right, and there are particles going from right to left. And these two classes of particles actually have different chemical potential, right? So one corresponds to the chemical potential on the lead, and the other corresponds to the chemical potential of left lead. So, and thus the system is perfectly ballistic. There is absolutely no way for these particles to thermalize. Means to give away their energy and to come to some sort of equilibrium, and therefore inside the quantum point contact, uh, we don't actually have a system that is described by a perfect Fermi distribution, but it's described by a sum, okay, of two Fermi function by a distribution function, which is not a Fermi function. So the Fermi distribution that is highlighted here is characteristics of the leads that are far away from the construction. This is also underscored in this slide, which shows that inside here, uh, I mean, here inside the ballistic region, trajectories are perfectly specular. Okay, and there could still, I mean, that you can see, it's completely specular, and there are then there could still be two classes of trajectories going from left to right and passing trajectories going from left to right, and scattering backs are not reaching the right contact, and the same for going from right to left. However, the process of giving away energy and becoming from new one losing energy down to view, that happens entirely when you approach the contact, when you leave the ballistic region, and that is what gives rise to this finite conductivity of electron square over h for a quantum point contact. Otherwise, there will, if there is a no dissipation, there would be no resistance, right? So hence no conductivity. So in this system, uh, so we saw that the temperature can destroy the quantization of the conductance. Here is another family of traces where independent of the temperature for a family of the temperatures from very low to fairly high conductance. Okay, in a very similar sample, a small constriction is not so perfect. There are many resonances. There are suppression of the conductance. There are enhancement of the conductance, and the traces look rather disheveled and disordered, right? So there are transmission resonances in the spectra, and conductance quantization as well is obscured by these resonances. Explanation for that is back scattering or finite transmission, you can say, of the constriction. Okay, so one way to get back the scattering, a very simple way, is to just engineer the potential such that it's very abrupt, and if you solve the Schrodinger equation to match this one-dimensional spectrum to this two-dimensional spectrum, there will always be a finite reflection that you can see here. Okay, reflection of, and this is very abrupt interface. But okay, in a real system, this is actually very hard because the two-dimensional electron gas is 100 nanometer below the surface. Therefore, uh, yeah. So perhaps in real experiments, most samples are allowed for a smooth transition from one-dimensional region to a two-dimensional region outside, right? So, however, backscattering is a very common problem illustrated here. For examples, if a couple of defects are located nearby the constriction, this trajectory will scatter a couple of times and this electron will go back through the constriction. Therefore, the conductance will be suppressed. In this case, can also be shown that the conductance can be enhanced if an electron that was supposed to be reflected off the wall scatters into the constriction. For example, if it is bounces many times back and forth, and so on. So this kind of disorder and backscattering will destroy the conductance quantization, right? And it will also destroy the the situation is especially severe if you are not dealing with a two-dimensional system. To Two-dimensional system dimension electron gas. But if you have a semiconductor nanowires, as shown here, in this case, you can try to tune basically a quantized constriction here. But as the electrons leave, they have such a small area to travel through that any small defect will cause the reflection back, and the electron will be scattered back into the constriction. So this kind of one-dimensional systems are very prone to resonances, while two-dimensional systems are less prone to resonances. Of course, it's all depends on disorder, right? So for nanowires, it's still possible to observe the conductance quantization. For example, is shown in the graph, but a very high magnetic field must be applied to the device. Yeah, same goes for the two-dimensional electron gas. They found already back in 80s that as they increase the magnetic field at zero test, so they could have a very disordered trace through. You could still kind of recognize the regions where conductance should be quantized, but as they increase the field that was applied the perpendicular to the surface of two-dimensional electron gas, so, like in the focusing geometry that we discussed already, eventually the filters become much more clear. So, the conductance quantization can be recovered by applying a higher magnetic field. And the physics behind this is suppression of backscattering by cyclotron trajectories. So if the electron flies through the constriction and it has to go always left, suppose it scatters here, it will not go back. I mean, it will just keep on going and skipping in circles in some directions, like that. So, like likelihood of backscattering is suppressed by a magnetic field that is applied perpendicular to the two-dimensional electron gas, right? Another effect, the out of plane field produces is the plateaus become more stretched. So again, this is some of the original data on the quantum point contacts. As they apply more and more field, you can see that the gate voltage requires to go from one plateau to other increases. I remember the gate voltage controls the effective size of the quantum point contact, or in other words, it controls the energy that is required. Basically, it's required to go from one subband to other. So if it takes more gate voltage to go from one subband to other, means that the subjects become more separated in energy. This effect, however, is not observed. And if the field is applied parallel to the two-dimensional electron gas, in this case, what you see in this graph basically is the that conductance goes from being to east corridor h to 1 to the square over h as the field is increased, and that is explained very simply by the lifting of the spin degeneracy at high magnetic fields, right? So degeneracy has been broken, and the subband number essentially doubles because the spin up and spin down do not have the same energy, and therefore the conductance become quantized in units of e square over h, right? But the size of the plateaus, the positions of all these traces are essentially unmoved. So the effect of perpendicular magnetic field can be accounted for by adding another energy term to the Schrodinger equation. Uh, I mean by adding a term that corresponds to the cyclotron frequency, right? So this magnetic field induced motion of electrons adds an energy scale, basically an energy scale to the harmonic oscillator, right? And makes the energy levels spaced by a larger distance. And so eventually you if you keep increasing the magnetic field further and further, you can even cross over to the quantum hole regime, or the plateaus turn into the eighth state of quantum hall regime, right?
Now, the conductance quantization has not only been observed in two-dimensional electron gas, also in as your semiconductors also been observed in metals, but in metals the energy and the correspondingly the length scale for observing this quantization are very different. Essentially, one conductance channel, one quantized conductance channel in a metal is one atom and its scale of one atom. So a couple of papers shown here show indeed the conductance quantization in the units of square over H. Here on the left, they have used the method where they have broken a strip of a metal, okay, by applying the strain basically to it, and they have observed in this kind of metallic one. Yes, so applying strain they have broken, and they have observed in this kind of metallic system two point contacts evidence for conductance quantization, but the constriction was so thin that it's only constituted a few atoms in width, and the same finding were confirmed this experiment and many other experiments in us. So where they crushed the chip basically of a chip of a scanning tunneling microscope into a surface of the metal, and they pulled the tip out, and as they pulled it out far enough such that there's only maybe one or two or three atoms left in the constriction, they could see how the conductance becomes quantized, and as a function of time, as the atoms leave and rearrange the conductors drop, and always in the units of the conductance quantum, that is squared over each, right? So the reason for this is that the Fermi energy in metals is much higher, therefore and the wavelength of the electron is much lower, of the order of 1 angstrom of your order of one atom size. Therefore, to see the conductance quantization, one has to go down to a few atoms in constriction with uh, yeah. So this is the probably last slide I'll show you on this thing. So okay, for the next part of this topic we discussed very neat, I mean, experiment that shines a lot of light onto the ballistic and coherent quantum transport of electrons in two-dimensional electron gas system, right? And in quantum point contacts, in this picture you can see that they were able to image the trajectories over which electrons travel in a two-dimensional electron gas. So these are beautiful experiments here. So the bright colored is showing this reverse that branch out, that is where electrons prefer to flow, and from a non in a nominally complete ballistic system, you can see that they prefer certain paths and there are certain branches which correspond to perhaps a few scattering centers that are observed here. Another thing is that you can see in this wonderful set of data is a set of interference fringes, and this interference fringes are quantum wave interference of electrons with themselves. So these are coherent uh, manifestation of the wave nature of the electrons in this two-dimensional electron gas. So the period of the fringes corresponds to the forming of the Fermi wavelength in this sample, right? So this is really a beautiful experiment which is related to this wave nature, right? So with this, I would like to end today's session, and I hope I have covered most of the topics on or the rather the basically the concepts which are very related to the all the assignment questions. So if you carefully go through this lecture and this session and go through all the slides, I guess you will be able to solve most of the questions. So I will again meet you guys on next Saturday. Thank you for your attention.